Hi all. In this video, we'll explore hydraulic pump head calculation step by step. To select a pump's capacity accurately, it's crucial to calculate the required head. We'll discuss the necessary formulas for this calculation and how to apply them. Head loss in piping systems. When supplying water to equipment like pumps, AHUs, and FCUs, pressure loss occurs in pipelines due to fittings such as bends, valves, reducers, and Ts. This is referred to as head loss. Head loss is a significant component in calculating a pump's total head. If not calculated correctly, it can lead to improper pump selection, resulting in inadequate design flow for the system and potential energy losses. Components of head loss. Before proceeding with calculations, let's understand the following types of losses. Friction loss, velocity head loss, fitting loss, static head loss, friction loss. When an object is pushed over an uneven surface, frictional force arises. Similarly, even if pipes have smooth surfaces, they poses internal irregularities. This means the internal surface isn't perfectly flat but rough or uneven. These surface irregularities increase friction, affecting water flow and causing pressure loss. This concept is utilized when calculating friction loss in pipes, represented by the roughness factor. For instance, steel pipes have a roughness factor of 150, while plastic pipes have 140. Velocity head loss. When water flows from a larger pipe to a smaller one, a pressure change occurs. In the larger pipe, the water flow pressure is higher. As the flow moves into the smaller pipe, the reduced size increases velocity, leading to a pressure drop. This pressure drop is termed velocity head loss. It increases resistance and friction in the water flow. Fitting loss. Water flows smoothly within pipes, but when it encounters fittings like bends, valves, reducers, and Ts, these act as obstacles, causing sudden direction changes or turbulence. This results in pressure drops, known as fitting loss. For example, when a butterfly valve is partially closed, it obstructs water flow, creating disturbances as water passes through the valve. This disturbance is called turbulence or turbulent flow. When water particles move randomly and swirl, pressure loss increases. In contrast, when water flows in a straight path before a fitting, particles move parallel and smoothly. This is laminar flow. Laminar flow has lower friction loss, whereas turbulent flow has higher resistance, leading to greater pressure loss. Flow classification using Reynolds number. To classify flow types, we use the Reynolds number, a dimensionless number determined based on flow velocity, pipe diameter, and fluid viscosity. Reynolds number less than or equal to 2300 laminar flow. 2300 Reynolds number 4000 transition zone. Reynolds number greater than or equal to 4000 turbulent flow. As the Reynolds number increases, the flow becomes unstable. Static head loss. Static head loss refers to the energy required to lift water to a higher elevation when supplying from a pump. The pump pushes water against gravity. This is the static head. In some systems, a booster pump is added, especially when the main pump cannot overcome the elevation. Calculating pressure loss using Hazen-Williams Equation. To accurately calculate a pump's pressure loss, ASHRAE recommends using the Hazen-Williams Equation. This equation considers water velocity, pipe diameter, water density, pipe surface roughness, gravitational force. The roughness factor varies based on pipe material. For steel pipes, the C value is 150, for plastic pipes, it's 140. Let's look at a sample calculation. As shown in the drawing, we need to consider all the pipes and fittings in this isometric view. Using this isometric drawing as the base, we will calculate the friction loss and total head loss using the Hazen-Williams equation. As we saw earlier, the ASHRAE formula is used in this calculation. The formula for fittings loss is shown here. The K value used in this formula varies depending on the fitting size, as per ASHRAE. The values are given in the table shown. Let's start with the first pipe. Given pipe diameter 250 mm. Water flow rate 71.67 liters second. To calculate the velocity, we use the formula. V is equal to QA. This gives us a water velocity of 1.409 meters per second. The pressure drop is calculated as 75.74 pascals per meter. For a pipe length of 7 meters, the total pressure loss is equal to 75.74 times 7 is equal to 530 pascals. In this calculation, the C value for chiller pipes is taken as 130. For condenser water pipes, it is taken as 100. The reason, condenser water systems are open circuit systems, and debris from outside can enter the pipes, increasing the pipe surface roughness. So, with a C value of 100, and using the same flow rate and pipe size, the pressure loss is 85.98 pascals meter. For a pipe length of 8.5 meters, the total pressure loss is equal to 730.83 pascals. Butterfly valve. The K value for the butterfly valve is taken from the supplier catalog. For the valve size mentioned below, the supplier K value gives a pressure loss of 312 pascals. Another example, FEP pipe. Pipe size 50 mm. Flow rate 0.500 liters second. By calculating the pressure loss for each fitting and pipe section, the total pressure loss comes out to be 1684 pascals. The header pipe's static head is 312,914 pascals. Adding a 15% safety factor, the total head required by the pump is 350 kilopascals. As we've seen so far, we've clearly explained how to accurately calculate the pump head requirement, covering all types of head losses, friction loss, fittings loss, and static head. For more technical HVAC videos like this, please subscribe to the channel.